Alright, this video is about molecular geometry and polarity. And we'll start with the VSEPR theory. It is the leading theory on molecular shape. Lewis structures are nice, and we do need Lewis structures in order to predict the molecular geometry, but Lewis structures are two-dimensional, and we exist in a three-dimensional world, so we need to think about these molecules and how they exist in three dimensions, and the VSEPR theory helps us with that. So, VSEPR stands for valence shell electron pair repulsion. So on the outside of every atom, we have electrons. And on the outside of another atom, we have electrons. And so what's going to happen is when two negatively charged pieces try and get together, they are repelled from one another, causing the atoms to be oriented as far apart as possible. So in a nutshell, that's what the VSEPR theory is. The valence electrons repel each other, causing the atoms to be oriented as far apart as possible. And if we use that principle, we can figure out the three-dimensional shape of any molecule. All right, so we have our basic shapes here. These shapes don't have any unshared pairs on the center atom because those will affect the molecular geometry. So if we have a center atom bonded to only two things, the furthest apart they can get is in a straight line. And so this one is called linear. If we have a center atom, again, all of these include no unshared pairs. If we have a center atom and it's bonded to three atoms, they are going to space themselves out evenly, and we get a 120-degree bond angle, and that is called trigonal planar. So it kind of makes the basic shape of a triangle, and it's all in one plane, so still two dimensions there. Tetrahedral in chemistry, 4 is tetra, and so if we have a central atom bonded to 4 other atoms, it is called a tetrahedral. The bond angle is 109.5, and so it ends up in 3 dimensions, kind of looking like a tripod with something coming out of the top. If we have a center atom bonded to 5 things, it is trigonal bipyramidal, and basically it's because you end up with what looks like, there's your base, and you end up with a pyramid on top and a pyramid on the bottom. So 2 pyramids making that bipyramidal. And then, and this is for expanded octets because, again, we have 5 things bonded to that central atom. So, again, remember to watch out for phosphorus and sulfur when we talk about expanded octets. Octahedral is another expanded octet. This one has no unshared pairs, again, on that center atom, and here we have 6 things bonded together. So these 4 are in one plane, and then there's one coming out of the top and one coming out of the bottom. And this is called an octahedral because if you look here, it has 8 faces if you were to count them all up, and that's why it's called an octahedral. Well, what if we have unshared pairs on that center atom, and that's really the only place that it is going to have an effect, is if those unshared pairs are on the center atom. So if we have a tetrahedral, no unshared pairs, the bond angle is 109.5. If we go to ammonia, and when we draw this one, we end up with an unshared pair. This unshared pair is only attracted to that one nucleus, making it take up more space than a bonding pair of electrons. And so it forces the bonding pairs a little closer together and closes that bond angle. So instead of a 109.5, this one with the unshared pairs has a bond angle of 107.5 for the bond angle between the bonding atoms. And then if we have 2 unshared pairs, and this one would be like water, we have 2 unshared pairs. Again, these unshared pairs are only attracted to the nucleus of one atom, so they take up more space than the bonding pairs, and so it forces the bonding pairs closer together. And the bond angle of water, which is a bent structure, is called is 105 or 104.9. So the bond angle decreases between the bonding pairs of atoms as you add more and more unshared pairs. Let me go back. I don't think I talked about the name of this one, trigonal pyramidal. If you look at it without the unshared pairs on there, it kind of looks like a pyramid, and that's how it's got its name. And then bent is for water with two unshared pairs, but still four things around the atom. Okay, now if we have five things around a center atom, again, if it's all bonded, is a trigonal pyramidal, and that is with five things around a central atom, no unshared pairs. Again, if we have unshared pairs, and a lot of times on the AP exam they do ask about how unshared pairs affect molecular geometry. You're going to need to talk about three different points. They take up more space than a bonding pair, and that is because they are only attracted to one nucleus. And then, so it's because it's only attracted to one nucleus, and it forces bonding pairs to move closer together. All right, so if we have five things around a central atom, except one of those is an unshared pair, that unshared pair is going to take up more space because it's only attracted to one nucleus, and it's going to make the bonding pairs slightly closer together. And this is called a seesaw shape, and if you set it down on two ends like this and this, it would kind of look like a seesaw if you see the three-dimensional models. Then if we have five things around a center atom, but two of them are unshared pairs. The unshared pairs take up more space because they're only attracted to one nucleus, and therefore push the bonding pairs slightly closer together. And this one ends up looking T-shaped, and so that's what it's named, if you don't look at the unshared pairs. And then we have another linear. This one we have five things around the center atom, except we have three unshared pairs of electrons. And so when you just look at the bonding atoms, they are in one line. So again, we call that linear. All right, this is if we have six things around a center atom. Again, just like with five things around a center atom, these are going to be for expanded octets. And if we have a center atom and all of it is surrounded by six things and they're all other atoms, it's called an octahedral. If I have six things around a center atom, but one of them is an unshared pair, the unshared pair takes up more space than a bonding pair, and it pushes the others slightly closer together. This one ends up looking like a square, or it ends up as square pyramidal, because these guys are all in one plane, so it looks like a square bottom pyramid. All right, and then if we have a center atom surrounded by six things, but two of them are unshared pairs, we end up with square planar. These are all in one plane. So those are your shapes. You really just have to memorize them. And in order to make a determination on what shape a molecule is going to make, you have to draw the Lewis structure because you have to know how many unshared pairs there are. There is one other that I didn't go over here, and it has to deal with another one called bent. So we can have bent just like water, where you've got your two unshared pairs and then two atoms bonded, and that bond angle is that 105 degrees. Another thing for bent is if it's almost like trigonal planar, so it's three things around the center atom, and what we end up with, and this is just one of the resonance structures here, where we end up with a three things around the center atom. One of them is an unshared pair. That's also called bent. So you have a handout that I gave you yesterday, or at least our last time in class, that has all of these drawn on there. You can also find some other three-dimensional looks at these, and that may help you out in trying to memorize them. But you do have to know them. All right, now let's talk about bond polarity. If I take this molecule, hydrochloric acid is polar because it has a positive end and a negative end. The reason it has that positive end and that negative end is because the chlorine is more electronegative and is pulling on those electrons. Since the electrons spend more time with chlorine than with hydrogen, chlorine develops this partial negative charge, and hydrogen, because its electrons are spending more time away from it, develop this partial positive charge. A molecule's polarity is very, very important. Now, this is how we notate it. There is this plus here, and it's moving this way. So it tells us which end is positive and which way the electrons are being pulled. All right. So chlorine has a greater share in the bonding electrons than does hydrogen, and they develop those slight charges. And this symbol here is just the symbol for slight or partial. All right, to determine a bond, whether a bond is polar or not, you can look at the electronegativity difference. Now, this is a table that has all of the electronegativity values that are assigned to each of the elements, and you just subtract big one minus small one. And if it falls within a certain threshold, then you have a polar bond. Usually, if the difference is between, so electronegativity difference, if it's a very big difference between the two atoms' electronegativity, so anywhere above 1.7, it is considered an ionic bond. And what ends up happening is that the element with the higher electronegativity or attraction for electrons pulls so much on the other element that doesn't have as much of an attraction for electrons that it pulls the electron off, and then you end up with an ionic bond. If the electronegativity difference is between 1.7 and 0.3, then that bond is going to be polar covalent. So that means that one of the atoms is pulling on the electron more than the other one, but it's not enough to pull it off. So it's sort of like an ion, but not exactly. They end up with partial charges instead of full-on charges. And if the electronegativity difference is below 0.3, which is really hard when you're dealing with two different elements, then it is considered non-polar covalent. Now, molecular polarity is different than bond polarity. Molecules that have polar bonds can be polar. And when we say polar, another word for that is going to be that they experience a dipole moment. Di means two, and it's got two poles, so you've got a positive and a negative. And so what we have, and that is the same thing as something being polar, is that it experiences a dipole moment. If we look at hydrochloric acid molecule, it will turn to align with an electric field. So we have this polar molecule here with its partial negative end with the chlorine and partial positive here. If we put it within, and the molecules are all mixed up, but if we turn the electric field on, all of a sudden, all of the chlorine atoms, and those would be the side with the arrow, align and are attracted to the positive end, and all of those slightly positive hydrogens are attracted to this negative end of the electric field. Now, a molecule will be polar if the bonds are polar, and, it has to be and, the molecule is not symmetrical. So, if of all of our base shapes that have no unshared pairs on the center atom, these guys are all going to be symmetrical. So if they have polar bonds, and they are one of these 5 shapes here, then the molecule will be polar. But if you have unshared, I think I said that wrong. Let me try that again. All of these shapes are symmetrical, and so these guys will not be polar. What ends up happening is that the electrons are pulled in with equal force but in opposite directions, and so the dipoles cancel out. One good example of that is if I have carbon dioxide. If I draw carbon dioxide, it looks like this, and the electrons are being pulled by the oxygen. So they're being pulled in opposite directions. So these are polar bonds here between the carbon and oxygen on both sides. But because they're pulling with equal force but in opposite directions, the dipoles cancel out. And that's a phrase you need to remember. Cancel out due to molecular symmetry. All right, so carbon dioxide is linear, which is one of these shapes, and so it would not be, um, it would be symmetrical and would end up being a non-polar molecule. So carbon dioxide is a non-polar molecule. All right, so all of these shapes are anything with these shapes are nonpolar as long as they have, well, any kind of bond, polar or nonpolar. If it has unshared pairs, like water, water is very polar, and the reason is because this is not a symmetrical molecule. These unshared pairs of electrons are sitting there and make the molecule not symmetrical. The oxygen's pulling on these electrons this way, and kind of they're going in the same direction. They're not being pulled in opposite directions. So the dipoles do not cancel out, making the bent structure a polar molecule. Here's another example where I have boron trifluoride. It is a very symmetrical molecule. The BF bonds are polar, but because this is a symmetrical molecule, the dipoles cancel out, and this molecule is not polar. But what if I take a hydrogen and replace one of the fluorines with a hydrogen? Well, that changes the symmetry of the molecule. And so the electrons are not being pulled with equal force. So we end up with a polar molecule because this molecule is not symmetrical, dealing with the atoms that it's bonded to.